This week in lab we are going to be doing the free radical polymerization of styrene to make polystyrene. There's different forms of polystyrene. You have more of a fluffy type form, that's your styrofoam cups, and then there's a more dense form of polystyrene. That's more of a harder type plastic in like some of your cups and things as well. We're going to be making the more dense version this week. So this is the structure of styrene. So we'll be taking and polymerizing that using a radical. Before I get into the reaction itself, the first thing that we're going to be doing with the styrene is passing it through a column of alumina. And the alumina, its purpose is we are going to remove 4-T-butyl catechol that is present in the styrene that you purchase. This is a radical inhibitor. And it contains styrene. When you purchase it, it will contain this radical inhibitor because styrene will polymerize very easily on its own. It will find a radical somewhere that will get it started. You only need a small amount, just like one radical is enough to get it going, and it will polymerize. So to keep it so that you can purchase it and they can ship it to you, keep it from polymerizing until it arrives, they put 4-T-butyl catechol in there, radical inhibitor. What this does is soak up radicals and not let those react with anything. It will form a very, very stable radical once it reacts, soaks up a radical. Now, to do the polymerization this week, so after we remove the catechol compound, we're going to be using benzoyl peroxide as to generate our radicals to get us started. And you've probably heard that name before. Especially back in your teenage days. Benzoyl peroxide is often used to treat acne. So it's in a lot of your acne medications. But we're going to be using it as a catalyst today, this week, in lab. If you take benzoyl peroxide and just heat it up, we break the oxygen-oxygen bond, that's the weakest bond that we have, and we get radicals. Now this radical likes to fragment. It's going to kick out carbon dioxide. We're going to break this carbon-carbon bond here so that you make carbon dioxide that will bubble out, and we get a phenyl radical. That phenyl radical is the radical that's going to get our polymerization started. That's what's going to react with the styrene. This is our initiation step. This gets our radical going. Now when you react the radical with the styrene, we have to decide which of the two carbons of the double bond it's going to add to. So our phenyl radical here can add to the CH2 end, or it could have come in and attacked the CH end. But if we attack the CH2, that will leave us a benzyl radical, which is a more stable radical. So it's going to go and form this radical. Like I said, this is a benzyl radical. And that's got resonance into the benzene ring. Let me just draw here. If it had attacked the CH carbon, this is the radical that you would get. You'd have a primary radical, has no resonance. That is not nearly as stable as our benzyl radical, so we don't get that one. Now the benzyl radical is going to react with more styrene. And it will, again, is going to attack the CH2 because that will give us another benzyl radical. So these add, it's referred to as head to tail. This end is the head, and this is the tail that's hanging off, so it goes head to tail. You don't want head to head. If two heads come together, if CH adds to the CH, then you're going to again wind up with a primary radical that has no resonance. So these add head to tail. And we've generated another radical. I wrote initiation on that step. I'm sorry. Initiation was the benzoyl peroxide. That was initiation. This was propagation step. Now this reacts again with more of the styrene. Again, head to tail. Okay, and we have another radical. So this is going to keep going and going and going. Our chain just gets longer and longer and forms our polymer. A typical polymer will have molecular weights anywhere from 100 to maybe 400,000 molecular weight. So I can't draw out the full polymer. I'd be drawing here from here down to the Gulf Coast if I was drawing out the full structure of the polymer. Now, at some point, the reaction is going to terminate. The termination step, so our initiation was the benzoyl peroxide giving us a radical to get it started. That's the initiation. This was our propagation. And then at some point, we'll have a termination step. Termination is where two radicals find each other. There's some number of these out through here, so I'm just going to put parentheses with an N. There's some number of repeating units there. Termination step is where two of these radicals find each other, and then we no longer have a radical. So for it to keep growing and getting bigger, every time we do a reaction, we need to be generating a radical. But when two radicals find each other, then the reaction is terminated. So we will often draw the final product here. Like I said, I can't draw the full structure out. squiggly lines there just means it just goes on and on and on. And I have some number of these units here that are repeating. So I'm going to put that in parentheses with a subscript in. There's some number of these that are repeating all the way down the chain. Like I said, these typically have a molecular weight of anywhere from 100 to 400,000 for a molecular weight. So that's our polystyrene. You can form a lot of polymers in this by this method, this free radical polymerization. Let me give you a couple more examples of some other polymers. So this is the one again that we're making this week in lab. Let's see. Here's another example of a polymer that can be formed by free radical polymerization. So if you notice, there is some number of these units that are repeating. By the way, this polymer is polyvinyl chloride. You'll often hear it referred to as PVC. That's used to make PVC pipes, water pipes. Now, there's some number of these that are repeating. So if you look at that structure, you can figure out what the alkene that we would need to make this. If you pull this out, that repeating unit, the two carbons that are repeating, it's always two carbons that are repeating, and just put a double bond between those two carbons. So this is the alkene that we would need to make PVC using a polymerization reaction, a free radical polymerization. Here's another one that you're probably familiar with. This one here, this is Teflon. So used to create non-stick surfaces, so like Teflon skillet you may have in your kitchen. Teflon tape to wrap around connectors and such used in plumbing. Again, it's the two carbons that are repeating. You're always looking for two repeating carbons. And looking at the alkene that we would need to make this, if we pull that repeating unit out here, there's the repeating unit, and just put a double bond between the two carbons that are repeating. So this is the alkene that we would need, tetrafluoroethene, to make Teflon using a free radical polymerization. Okay, this is a very short lab this week. So as I mentioned there at the beginning, we'll have to remove the radical inhibitor. We're doing that using alumina. And we're going to use a disposable column this week, so not the column that's in your kit. We're going to use a Pasteur pipette this week. So take a disposable Pasteur pipette. You're going to put a little plug of cotton here in the inside. So put a small piece of cotton in. You can take your spatula or a boiling stick or something and push it down to the bottom. So you'll have the cotton in. You're going to fill this about half full of alumina. And then you're going to take 1.5 mils of styrene, put it on the top of the column, and let it run through. You're wanting to collect at least 1 milliliter into a disposable test tube. Now, make certain you're collecting it into a disposable test tube. We have those sitting out on the bench there in the lab. Make certain you use a disposable test tube. So this has removed our inhibitor, and then we'll do the polymerization. So you're going to add 50 milligrams of benzoyl peroxide and a wooden boiling stick, and then heat that over a sand bath. Polymerization should begin around 135 degrees. However, you are not going to put the thermometer in the reaction tube or in the disposable test tube. Otherwise, we'll have polymer all over the thermometer, and I don't want that. So just assume that it's 135 degrees. Once the reaction gets going, it's very exothermic, so it'll generate its own heat and continue to polymerize. The temperature will keep rising up to about 180 degrees. And the solution, if you take that boiling stick, you'll notice if you'll take and lift it up or stir it or whatever, the solution is going to get thicker and thicker as it heats. You want to monitor the polymerization using that boiling stick. Pull the boiling stick up out of the test tube, and the polymer, the polystyrene, should string off of it, form fibers. If it's not, it needs to cook some more. But when it gets thick enough, some of it was going to stick to the boiling stick, and as you pull the boiling stick out, it's going to form little fibers. You'll string off of the boiling stick. Allow some of those fibers to cool and test and see how brittle it is. If it breaks very easily, you're done. You've heated it long enough. If it's kind of sticky and gooey, then you need to heat a little bit more. So it should break very easily, some of those fibers that you pull out. So once you think it's finished, pull it out, let it cool, and then you're going to put it in an ice bath, and hopefully it will shrink down. Now leave the boiling stick in there, and we're hoping that the polymer will shrink down, and that you can then pull the polymer out using the stick. It should shrink onto the stick, and you should be able to pull it out like a lollipop. It'll look like a lollipop if it works well. Now, we've done this many times in the past, and oftentimes the polymer doesn't come out that easily. So if it doesn't, take it to your instructor, and we will take a hammer and break the disposable test tube. That's why we're using a disposable tube this week. We'll break the tube for you to get the polymer out. In your conclusions, discuss the texture of the polymer. Is it hard, brittle, sticky? If it's sticky, it means that you didn't heat it long enough, didn't cook it long enough. If it's extremely brittle, breaks very easily, means you overcooked it, cooked it too long, heated it too long. So you can talk about that in your conclusions. Okay, so this is a very short lab. It's a fun lab that we will end the semester on. So at the end of the lab, since this is a fun lab, I want you to, once you're finished, just quickly write a little short conclusions, show it to your instructor, and we'll give you, this week we'll just give you a free 25 points if you come and do the lab. Now, I've had a difficult time keeping up with everybody that has been quarantined and missed labs this semester. If you've missed one lab this semester, it will count as your drop lab. If you've missed 2 labs, email me and let me know. I've went through and I think I've gotten everybody, but I may have missed some. If you've missed 2 labs or more, please email me and let me know which labs you missed, and I will choose the lab that you're going to make up. We will do makeup labs this week immediately following the polystyrene lab. It's a very short lab, and you can also do a makeup lab. If you only missed one lab, I'm not going to let you do a makeup. That will automatically count as your drop lab. But if you've missed 2 or more, let me know which labs you missed, and I will choose the lab that you make up. I'm going to choose the shorter one or the one that's easier to prep. So it'll be my choice as far as which one you will be allowed to make up. But that's only if you've missed 2 or more labs.